Hello, and welcome to another episode of Risky Business. So last time, um, we looked through this program, and I believe we wanted to understand the logic here, and then as well as these things going on with these compare registers. I was thinking when we read the documentation that it was like every one of these, like there was one PWM signal that the hardware produced, and like could stack these compare registers on top of each other to make a complex waveform. But now I'm thinking that's not how it works just by looking at this code, because you see that compare one is doing something with G, just the G channel, and then 2 is doing something with just the B channel, and then 3, you see it's only messing with R. So just, glossing over that code, it suggests to me that we're producing 3 different signals for each pin, and these control the different signals. So that's kind of what's brewing in my head when I see that before we actually dive into it and really figure out what's going on. But before we get into that, I want to look at this logic here. So let's see what this is doing. It's saying if R is greater than 0 and B is 0, then it lowers the brightness of the red channel and increases the brightness of the green channel. So this is going to fade from red to green. So we started at red as being FF, green as 0, blue as 0. So it starts out as red, and then it fades to green, because this path is going to get taken until the red channel gets turned off. And at that point, the green channel will be at FF, right? And then it's going to end up taking this path. So it's going to say green is greater than 0 and red is 0. So it's going to lower the brightness of green and increase the brightness of blue. So this is just going to fade from green to blue, right? And then it's like the same exact thing that happened right here, just with different colors. And so then finally we're doing the same thing for when blue is greater than 0 and green is 0. So in that case, we're increasing the brightness of red and decreasing the brightness of blue. So it's going to fade from blue to red, and then it would go back to this one. So it cycles from red to green to blue back to red. So let's plug in the Hi-Five 1 here and just eyeball it and see that it's actually doing that. So I can't show you my Hi-Five 1 while it's running because the cable that I'm using, the USB to micro USB cable, I have it plugged into the back of my PC because we found out those front parts aren't good. But as a result of that, I can't really reach it up here to show you. I'm kind of thinking maybe I should get a second webcam so we could have another webcam to show, like Hi-Five 1, or if I'm working on my desk, show something like that. I think that might be a good investment. But for now, you'll just have to take my word for it, or if you have a Hi-Five 1, you can try it yourself and see. So I think this program we currently have on the board, I could be wrong, but I think that was the last thing we messed with. So I'm just going to plug it in and see if it starts fading the LED. So it did not fade the LED, so apparently this is not the program that I have on this Hi-Five 1 right now. So, let me just make sure that we didn't, like, do anything that breaks it. No, it should be good. So let's just upload this program to the Hi-Five 1. So let's do a make software clean. It looks like the last thing in my history here was building demo GPIO. So we're going to build LED fade. All right, and then we are going to upload that. I haven't checked the Hi-Five forums lately. I don't know if that's that issue we occasionally have when we try to upload. I don't know if that's been resolved or not. So anyway, we uploaded. So I see it's doing the fade now. So I'm going to hit reset and keep a close eye on it to see if it's doing what we expect. Yes, it is going red, green, blue, and then back to red. So it is doing exactly the logic we expected. Here, let me move this Chrome tab. Have that open so I can do a hangout if necessary for work. So I think we understand all of this. So the last thing I want to understand is this stuff we're doing with the PWM Compare 1, 2, and 3. And then we also should look up these constants and make sure they're the values we expect them to be. So, okay, so it was the E300 manual that has the PWM related stuff. So we've got these PWM Compare Registers. So the width of these registers should be compare width, which is presumably 16 on the Hi-Five 1. The comment suggest that, but we're not going to go off the comment. The comment here says period is approximately 244 hertz, which would suggest 16. The reason I say that is because it was mentioned somewhere in here, right here, at a 16 megahertz bus clock rate with a 16-bit precision. The fastest PWM cycle would be 244 hertz. So presumably we have 16-bit precision. And we know we're setting the 16 megahertz bus clock rate because that's the reason where we use the LED demo to check the values in the OTP, because that speed is slow enough to get proper reads from the OTP. So if we're talking about 16-bit registers, these PWM Compare Registers, then it's kind of weird to me that we make these 32-bit variables, because these lowercase ones you see here, those are 16-bit, which makes sense because 16-bit compare registers, right? So then I don't understand right now why these are 32-bit. We should probably take a look at the macro to see what exactly it's doing. So, I mean, one thing is the actual registers, you see this in the thing, the actual registers are 32 bits, right? But the high end of the register is reserved. The only stuff we care about is the low end. So I guess in terms of accessing the hardware, we read an entire 32 bits. But it's only the low end that has the actual value we care about. So I think that's probably why it's 32 bits. I'm guessing this PWM1 reg macro works the same way as the GPIO one and probably uses 32 bits. So let's see if we can find out. So what all do I have open here? There's a pwm.h. Let's take a look at that right away. Okay, so we have the constants for the various config register bits, right? They're all defined right here, and you could find that those should match up with the documentation right here, right? So here's the PWM config register. I was thinking they were going to write these constants as one shifted left by the bit position. That would be the readable way to write this, but they've actually just written out the hex constants here. So like config scale has F in the low, so that would be 4, right? Or like, I mean, like binary 4. Like not the number 4, but like the fourth place, like one shifted left 4, I think would give you an F in this place. So would that make sense? That would give you reserved. So I might be wrong about that. PWM config scale. Zero xf to binary. I want to see it in binary. I think it's just like 100. Oh, it's 1111. That makes sense, actually. Yeah. So if you're saying scale, PWM config scale, is this not a mask to the location of scale? Because scale, PWM scale is 0 to 3. So you'd think it would just be 0 or 3. You know, either one. Or I mean, like if it's 3, we'd want it to be like 100 as the mask, right? But we've got this this 15 in decimal. So like if we said 1 shifted left 15, if we're talking about like the mask, that would be like way over here, and this is reserved memory too. So what are these constants then that we're looking at? So we have sticky is 100. And it's the 8th bit. So I mean, if we say like that's 4. I mean, I guess I did need to do that. But I'm not seeing the correspondence between these values and the locations in the registers. So I'm confused. What do these constants represent? Like the register offsets, those should be straightforward. So like let's take a look at those first. So here are the registers and here are the offsets. Config is 0, count is 8, scaled is 10, and then the compares are 20 to 2C. So 0, 8, 10, 20 to 2C, right? That's really straightforward. That's just straight out of the documentation. So what's going on with these bits is my question of the day. So, I mean, the maximum value of 15 in PWM scale. So, like, I mean, it has 15 possible. I mean, like, it's 4 bits, right, for PWM scale because it's 0 to 3. So that's 4 different bits there. And this constant is 4 ones, but what would you use that for? Like, I don't understand. I mean, I guess you could say if we're talking about a mask, then the bits that are on in the mask, those 4 bits correspond to the 4 bits in PWM scale. So I guess that would make sense actually. But then PWM sticky is the 8th bit here. But we're setting 100. So, I mean, like in hex, each digit is a nibble, which is 4 bits, right? So this is 4 bits, this is 4 bits, and then this is like the low bit of the next 4. So that's the 9th bit, I guess, would be the mask there, which would be correct because we're counting from 0 here. So this is the 9th bit. So I guess it is masks. It's just confusing me because it's written in hex instead of just being like one shifted. And also the fact that when you have a mask for a range of bits like PWM scale, rather than being one shifted left by so many, it's actually masking every bit in the range. So I understand what's going on here now, and we see that these first two values correspond. 0 compare, let's do that one quick. That one's the one right next to sticky, and that's what we see in the code. Deglitch is a couple over from that. So wait a minute. This was 2. Oh no, yeah, because 4 is 1 place over in base 2, right? So this is 1 bit over from 2. It increments in powers of 2. So 1, 2, 4 is 3 adjacent bits, and that's what we see in here. Enable always. We skip the next power of 2, which is 8. So you see here it's reserved, and then there is enable always, and that's what we see in the code with this being 1. Then we have an adjacent one, which is 1 shot. That's what we see. Then we have reserved, and then compare 0 center. So you see we don't see a 4 here, but we see a 1. So that would suggest that there's 2 bits that are reserved. Are there 2 bits that are reserved? Yes, there is 14 and 15 bits are reserved. So that makes sense. So then we have 3 adjacent, actually 4 adjacent, and then 4 more adjacent, and then 4 more adjacent. So the rest of them are adjacent. So these 4 are adjacent. There was reserved between 20 and 23, but these ones are all adjacent. So I didn't spot the reserved memory in here. Where was the reserved? Okay, it's right here between compare 3 center and compare 0 gang. You see we skipped a nibble. So there's reserved memory between compare 3 center and compare 0 gang. looks like 4 bits, and that's exactly what we see. So, okay, we fully understand the constants. These are masks for the different bits in the config register. And we understand the register offsets, which correspond directly to this table here. So I don't know if this documentation specified the base address of the config register. That might be platform dependent? Question mark? Yeah, I'm not seeing, if it's defined in here, I'm missing it, because I'm not seeing it. Excuse me. So let's take a look at the documentation for the chip. So probably the memory map. Okay, so we do see some PWM stuff in this memory map here. We see PWM 0, PWM 1, and PWM 2. This is an 8-bit timer with 4 compare. This is a 16-bit timer with 4 compare. And this is a 16-bit timer with 4 compare. So that's interesting. One of the PWMs is actually only 8 bits. They're not all 16-bit. So they actually have differing precision. So we're using PWM 1 for all 3 of these, because you see we're using the PWM 1 register macro. Okay, so that's interesting. So we have 3 different PWM hardware support, but we're only using one of them. We're using PWM 1. So the base address of that would be 10025000 in hex. It's a 16-bit timer, which is what we expected. And it says it has 4 compare. So I guess compare 0 to compare 3 is what they're talking about there. So then, that's interesting to me. The fact that we have 3 different PWMs, I was thinking that we're producing 3 different signals for the different channels. But this suggests to me that if we wanted to produce 3 different signals, we could definitely do that, because there's 3 different PWM hardware things. But we're only using one PWM peripheral. We're using PWM 1, which is the first 16-bit one. So maybe we only produce 1 signal, and it's driving all 3. I still don't totally understand this whole PWM compare business. And then we have these comments. PWM is low on the left. GPIO is low on the left side. LED is on the left. This one says PWM is high on the middle. GPIO is low in the middle, LED is on in the middle. And this one says PWM is low on the left, GPIO is low on the right, LED is on the right. Yeah, I still don't understand. um, so, I mean, we have 3 different pins, right? For like green, blue, and red. Is the LED driven with a single signal? I was thinking we drive the LED with 3 different signals. The signal for the green, the signal for the blue, and then the signal for the red here. Okay, and you see here in this table of the pinout, PWM1 is this block right here, and the LED is wired up to that. So you see the green, blue, and red are wired up to the PWM1, 2, and 3. So we are sending, these are different GPIO pins. We are sending the data over those. So there's 3 signals is what I'm saying. 1 for each channel, which is what I expected. So basically what we have here is there's 3 different PWM peripherals. There is PWM1, and it has 4 different signals that it can produce across different pins. There's 4 different pins, right? And the same thing is true for PWM0 and PWM2. So each compare produces a different signal across a different pin, is the idea here. So we have 1, 2, and 3 wired up to green, blue, red of PWM1. So then if we go back to the code, we see there's 1, 2, 3, and it's doing green, blue, red. So compare 1, compare 2, compare 3, green, blue, red. PWM 1, 1 is green, 1, 2 is blue, 1, 3 is red. So those match up. The compare register matches up with the documentation for the different pins for the different channels. So that much I think makes sense. So let's take a moment here and go back to what we were looking at. So we saw these defines and these constants. And where do we use these in the code? So we use the PWM config. We set it to 0. Then we set enable always and compare to center. So those are the masks that we saw. Compare to center right here, and enable always right here. And so those are being ORed together, and that's exactly what we expect. And then we set the count to 0. We set compare 0 to 0. and then we set 1, 2, and 3. So the next thing we need to understand is we want to take a look at the PWM1 register macro. So let's see if we can find that in the code. I'm going to check platform.h first. Okay, so here's the PWM reg macro, and you see it's using the reg32 macro, which is the exact same macro that we used for the GPIO reg macro. So this works exactly the same way. It's adding the pointer and the offset, the base address and the offset, converting it to a pointer, and then dereferencing it. So we're adding the PWM1 base address, which I believe we saw, didn't we? Let me double check that. I'm not sure if we actually saw that in the code yet. No, we didn't see the base address yet. So we need to look up that. And then we had the offset. And so we saw the offsets that we're passing in, and we saw where they're defined. So we understand that much. So right now we need to find PWM1 base address. So let's search for PWM1, and there it is right there. So it's 1002.5000 in hex. And I believe we saw that in the documentation right here. 1002.5000 hex is PWM1. So that lines up with the documentation. And then these AC macros, I remember, are just like, depending on compilation flags, it appends the UL to the end of the constant, which we don't really care about. So I think we understand everything the code's doing. It's just a matter of understanding what we're doing with these 3 lines right here. So we know that we're producing signals for the green channel, the blue channel, and the red channel. We know that we've got a 32-bit register in each. That's the compare register. And the 16 bits, the low 16 bits of the register are the actual compare register that we care about. The high bits are reserved. And so it seems that these uppercase GRB are just convenience casts. Like, we're just doing that as a convenience to get them in 32-bit registers. So when we say compare 1, G shifted left 4. So we need to take a look at the compare register documentation again and see if we can really understand it and understand what's going on here. See, this is the thing I'm confused about, though, this concept of ganging. They talk about how a comparator can be ganged together with its next highest numbered neighbor to generate arbitrary PWM pulses. Well, we're not setting the PWM compare gang bits. So I think you can use the compare registers, like chain them together to get arbitrary waveforms like I was thinking about. I think that's this ganging that they're talking about. But you don't need to use them that way. You can use them to generate separate signals. Um, so because we don't set this bit, we're not using it in this ganging form. So then where was the documentation on the compare registers? So the use of these registers is to define the edges of the PWM waveforms within the PWM cycle. That's what we expect them to do. So they're compared against the current PWM S value every cycle. So the output of the comparator is high when the value of the scaled PWM counter is greater than or equal to the value in the compare register. So we're producing a high signal whenever the counter is greater than our what we're comparing with, and we produce a low signal when it's less than this value. So let's take a look at the PWM scaled register again. So we have the count register, which is the actual unscaled value. It's a 32-bit register, but it only counts the first 31 bits. It's actually 15 plus the compare width, so it would be less than that for the 8-bit counter. Or I mean the 8-bit PWM thing. But we're using one that has 16 bits of precision, so we do have the 31 bits of PWM count. So this is going to increment every cycle. And then we're using it scaled, of course. So we're not using one-shots. We're not using the 0-bit, whatever that was called. So I guess in this diagram here also, we see here the outputs, these arrows going out of all of the different ones. But then you see it can also be ganged together, so it goes over compare 0 and makes a more complex waveform, I guess. So we are using enable always, so the counter increments continuously. So the PWM scale field scales the PWM counter value before feeding it to the PWM comparators. The value in PWM scale is the bit position within the PWM count register of the start of a compare with bit PWMS field. So the PWMS field is going to be 16 bits. And so our counter is going to go from the, like, if we look at the counter register, I guess they don't diagram it, but it's just like a 32-bit register. We're starting, because we don't set an offset with this PWM scale, we're starting at just the low bits, and then looking at the first 16 bits. But without setting that 0 bit, doesn't it keep counting past the 16 bits? So I think when we look at the scaled PWM value, the value in PWMS, we see a 16-bit value, but the counter is counting on the 31 bits of precision. So, like, after you get to the full maximum value within the 16, it's just going to stick at that value until the counter gets to like 30, like the full 31 bits, and then it's going to reset to 0. So I think there's a period where it just sustains for a little bit. If I'm understanding that correctly. Yeah, so it says the PWMS would be equal to the low compare with bits of PWM count. So the low 16 bits of PWM count. And then they say, this is the thing I was wondering about, the 0 compare bit. It causes PWM count to reset to 0 after the PWMS counter matches the compare value. Okay, well, I was thinking it would reset after the 16 bits, like after the compare with, like when that would overflow if it was actually a 16-bit number. I was thinking that's when it would reset the counter, but this is saying it resets it after the values match with the compare. But we're talking about compare 0 too. I still don't fully understand the use of compare 0 compared to the 1, 2, and 3, I guess. So let me read this count thing again. I want to see, does it reset based on scaled, or does it just wrap around with the full 31 bits? It says, when used for PWM generation, the counter is normally incremented at a fixed rate. Oh, it's reset to 0 at the end of the PWM cycle. The PWM counter is either reset when the scaled counter PWMs reaches the value in compare 0, or it's simply allowed to wrap around to 0. So it seems like PWM Compare 0 is used to set the width of the cycle, like the what was the term? Let me fire up Milton. The duty cycle. It seems like Compare 0 is being used to set the width of the duty cycle, if I'm understanding correctly. And if you, I guess if you don't use it for that, it's allowed to just wrap around to 0. So that means for the scaled value to wrap around to 0 is when the PWM counter resets. I think that's what's happening, that the counter resets after the PWMS value wraps around to 0. And it can also reset to 0 before that by using this Compare 0 register. So with that in mind, let's go over the compare registers another time. So the use of the compare registers is to define the edges of the waveforms. Each register is compare with bits. So for the most part, it seems like PWM 0 compare 0 can be used just like the other compare registers, generating a signal. But it also has this behavior where you can set the 0 compare bit and use it, I guess, to control the width of the duty cycle. I think that's the idea there. And then there's this deglitch and sticky circuitry stuff, which we're not messing with. So generating left or right aligned PWM waveforms. So like here they're saying they're using a 7 clock PWM cycle. They set the value in PWM Compare 0 to be 6. Right, so they're controlling the duty cycle here, the PWM cycle, as they call it, to be this particular length. And they're doing that by setting Compare 0 to 6. And so they must be setting the 0 bit then too, right? Because I think that's what's used to control that behavior. Yeah, that's when the PWM 0 compare bit is set. So in this example, they're setting the PWM cycle by turning on the 0 compare bit and then putting 6 in the compare 0 register. so that you get a 7 clock PWM cycle. So that makes sense to me. And then the interesting thing here is the interesting thing to note is the signal is high most of the time. It's when your value, when it's less than your value, it it drops the line low, but normally the line is high with these waveforms. So it's kind of backwards from what I'd imagine in my head. Like, you'd think that the more the waveform is on, the brighter it would be, I guess. Like, I'd expect that the amount that it's on would correspond directly to the brightness that it produces. But this is kind of telling me it's backwards from that. But then you also have to consider that we're doing some bit manipulation here. So maybe that's not true. I think the bit manipulation is probably due to the fact that this is kind of backwards from what you expect, the way that it's high by default instead of low. I have a feeling that's why we're doing bit manipulation. So let's think about the logic that's happening here. So if we say G shifted left by 4, so we're taking the value in G and we're doing these 8-bit values even though it's a 16-bit register. So like FF is 255, right? So that's like a hex code like color, right? So R being 255, that's like red is fully red. And then the green and blue channels are off. So if we take the value FF and then we shift it 4 places to the left, so that's like one nibble that we're shifting. So, I mean, I want to draw this out, I guess. So we're going to say we have a 16-bit register. So I'm going to say like, I guess I'll just draw a bunch of zeros to indicate the different bits. So this is our 16-bit register. right? And so when we say FF, we're saying this value right here. And then when we shift it left 4 places, we're saying this value right here is what we get. So like if we set the green channel to be FF, the thing that we're passing into the compare register is this value right here, the FF0. So it goes from 0 to FF, or I mean, I guess I should say like when we do 1, it's going to be 1 0 0x 1 0, right? Would be the low end, and then the high end is this 0x FF0. So that's kind of the range of values that we're getting. And so it's saying while it's less than those values, while the counter is less than those values, it should be off. And when it's greater or equal to that, it should be on. So I think we actually want to draw out the waveform to really understand this, right? So it's a 16-bit counter, and we're not scaling it. So, I mean, the counter is 32 or 31 bits, but we're using the low 16 bits, right? So, for our purposes, it's a 16-bit counter. So, for the 16-bit cycle, we want to see how much of it is on and how much of it is off. Like we want to see a diagram of the waveform this is going to produce, and I think I can draw that out for you guys. But I think we're also out of time for today, so I will have to do that in the next episode. So thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me on Twitter at HMN_risky to get updates about the series. I will see you next time, and stay risky, everyone.